The paper is JetRL, Enabling On-Policy FP8 Reinforcement Learning with Unified Training and Rollout Precision Flow, from researchers at NVIDIA, MIT, UC Berkeley, and Stanford. Here's the bottom line. If you are training reasoning models, things like DeepSeek R1 or large chain of thought systems, you are absolutely bottlenecked by the rollout phase. It's probably eating up to 70% of your training time. Now, the industry standard fixed running rollouts in FP8 while keeping training in BF16 is, it turns out, technically broken for long contexts. It causes policy mismatch, and it leads to model collapse on sequences longer than about 8,000 tokens. The solution proposed here, JetRL, introduces a unified precision flow. By forcing the training forward pass to use the exact same FP8 quantization graph as the rollout, they restore what's called on-policy consistency. The results are pretty significant: a 41% speedup in training, a 33% speedup in rollout, and less than 1% accuracy degradation on really hard tasks.
It basically solves the instability of low-precision RL. And it proves that consistency, actually matters more than just raw precision.
Okay, let's unpack that. Because, if you're an ML engineer working on post-training right now, especially for reasoning models, this paper is aimed squarely at the single biggest pain point in your entire pipeline.
It absolutely is the bottleneck. We're in this huge shift, from what you'd call System 1 models, the fast, intuitive ones, to System 2 models, the ones that think and plan and verify.
And to train those, you need reinforcement learning. You need the model to generate just a ton of tokens, explore different paths, and then get feedback.
And that generation part, the rollout,
yeah,
it's just so slow.
Excruciatingly slow.
It has to be serial. You're generating token by token, one after another. The paper points out that for these long reasoning chains, 6,000, 8,000 tokens, the rollout phase is over 70% of the total end-to-end training latency. So you're spending the vast majority of your GPU budget just waiting for the motor to finish its thought so you can actually do the update.
So naturally, everyone in the industry looked at that and said, okay, let's quantize it. It's the standard playbook. You move from BF16, that's brain floating point 16, down to FP8. You basically double your throughput on an H100, cut your memory usage in half, and in theory, everything just gets faster.
Right. And just to be clear, this is the default. It's the default behavior in major frameworks like VRL and OpenRLHF. It's what we call the hybrid strategy.
Hybrid, okay.
You do the really expensive generation, the rollout, in fast FP8, but you keep the critical parts, the gradient updates, the reference model, in high precision BF16.
The thinking being, I want speed for all the heavy lifting, but I want to keep precision for the actual learning part.
Exactly. It makes a big assumption that the quantization noise, the tiny little rounding errors you get from using 8 bits instead of 16, is basically negligible. And for a long time, that assumption was fine. If you're summarizing an article or running a chatbot where the answer is 500 tokens, the error just doesn't have time to build up into anything meaningful.
But this paper really throws a wrench in that. They're showing that when you push into that deep reasoning territory, we're talking 8K, 16K tokens, that hybrid strategy just completely falls apart.
It's a silent failure too, which is the scary part. They showed these experiments on Qwen3 HB base. When they trained it on math problems with short answers, everything looked great.
Okay.
But as soon as the reasoning chains hit 8,000 tokens, the accuracy started to get wobbly. And at 16,000 tokens,
what happened?
The model just collapsed. It completely stopped learning after about 20 steps.
So it's not just a little bit worse, it's non-convergent.
It's catastrophic, yeah. And the fundamental reason, is something called policy mismatch. In RL, you have this core requirement that your training data has to be on policy. The data you learn from must come from the exact same policy, the same brain that you're trying to optimize.
But with the hybrid approach, you have a numerical discrepancy. You've got an inference brain running in FP8 and a training brain that thinks in BF16.
Exactly. The inference brain sees the world through this quantized, lower resolution lens. It makes its decisions based on that grainy view. But then the training brain tries to update the weights based on its high-resolution, perfect view of the world.
So for short walks, the path is close enough.
Close enough. But for long chain of thought, those tiny deviations at every single token step, they start to compound, they snowball.
It's like the butterfly effect, but for floating point math.
It's a perfect analogy. By the time you get to token 8,000, the trajectory that the FP8 rollout generated has drifted so far from what the BF16 training model would have done. The probability distributions just don't match anymore. So the gradients you calculate are, well, they're pointing in the wrong direction.
You're essentially training the model on hallucinations caused by its own quantization error.
That's it.
This is a huge deal. The entire field is pushing for longer and longer context. We're seeing these R1 style models that have massive internal monologues. If the standard FP8 rollout breaks at 16K tokens, we have a major infrastructure problem.
We really do. And that's where JetRL comes in.
Yeah.
And their solution is so interesting because it really challenges that core intuition that higher precision is always better for training.
Right. Their fix is this unified precision flow.
Exactly. They basically said, look, if the mismatch is the problem, then we have to eliminate the mismatch.
Yeah.
And since we can't afford to run inference in slow BF16,
we have to degrade the training forward pass to match it. Make it FP8 too.
you have to.
That sounds incredibly counterintuitive. You're intentionally adding noise and error into your training loop.
You are. But here's the key.
Yeah.
You are adding the exact same noise that the model will see during inference. They treat the inference process as a strict subgraph of the training process. This makes sure the training model experiences the quantization error. It learns how to navigate the world with that noise.
So train how you fight. If you're going to fight in 8-bit, you have to train in 8-bit.
Precisely. By unifying the precision, that policy mismatch just disappears. The model becomes robust to the quantization because it's no longer a surprise. It's just part of its environment.
I want to get technical here for a second because I know our listeners are engineers who are probably thinking about how to implement this. You can't just call model.to FP8 and expect it to work, right? The paper spends a lot of time on the specific quantization granularity.
Oh, absolutely. Section 4 is basically the implementation guide here.
Yeah.
And you're right. Standard per tensor quantization, where you have just one scaling factor for a whole weight matrix, is way too rough.
It kills the outliers.
It kills the outliers and the activations, which are absolutely critical for complex reasoning.
So what's the JetRL configuration then?
They use a mixed granularity approach. So for the weights, they use block quantization, specifically 128 by 128 blocks. They chop the matrices into these little tiles and scale each one on its own. It preserves the fine-grained structure.
Okay, that makes sense for the static weights. What about the activations? They're dynamic.
Right, activations are trickier. For those, JetRL uses per-group quantization, specifically 1 by 128 groups. This lets the quantization adapt on the fly to the actual tokens flowing through the network.
Now, here's the part I found really clever, the backward pass. We know they quantize the forward pass to match rollout, but what about the gradients? If you quantize gradients too hard, they can just vanish.
That is the classic underflow problem. The gradients, especially late in training, can be incredibly small numbers, like 10 to the power of -6 or 7.
And if you try to cram that into an FP8 format, it just gets rounded to 0.
And if your gradient is 0, you stop learning.
So how does JetRL solve this? How do they handle the backward pass?
They do something really smart. They split the difference between communication and computation. The communication of the gradients, the actual values being passed between the layers, they keep those in BF16. This preserves the signal, its magnitude, its direction.
But the heavy lifting.
But the heavy computation, the actual general matrix multiplies the GMMs to calculate those gradients. That's all done in FP8.
They mention the 3 big GMs, F-prop for the forward pass, D-grad for the input gradient, and W-grad for the weight gradient.
Right, F-prop is fully quantized, that's the whole point. D-grad reuses that kernel configuration.
Yeah.
But W-grad calculating the update for the weights themselves, that uses a very specific trick they borrow from the DeepSeek V3 architecture.
The alignment trick.
That's the one. For the weight gradient calculation, they align the matrix dimensions as 1 by 128 against 128 by 1.
A dot product alignment.
Yeah, it's a dot product alignment that mathematically minimizes the quantization error for that specific critical operation. It's just a really elegant piece of engineering. It shows they aren't just blindly applying quantization, they're tuning the math for the physics of the backward pass.
And this is why it's so important to read these papers, because these little tricks, like that W-grad alignment from DeepSeek, they become the new standard primitives for building efficient training systems.
It's totally true. It's not enough to just know the high-level architecture anymore. The real gains are happening down at the kernel level.
So let's get to the results. They ran this on Llama 3.18b and Quinn 2.5 SESNB. We already know the naive hybrid method crashed and burned on the long context tasks. How did JetRL do?
It was seamless convergence on the exact same 16,000 token tasks where the old method just flatlined. JetRL tracked a full BF16 baseline almost perfectly, like pixel perfect on the loss curve.
And what about the final accuracy?
So they tested on deep math, which is super sensitive to precision because, well, it's math.
Right.
The naive method dropped about 10% in accuracy compared to the baseline, which is a total deal breaker. JetRL was within 1% of the baseline. In some runs, it was basically statistically indistinguishable.
So you get the stability back. But the whole point of doing all this was for speed. What was the payoff?
The payoff is huge. They report a 1.33x speedup in the rollout phase alone for 32B models. But, and this is the part people might miss, because they also quantized the training forward pass. The training phase itself got faster.
By how much?
About 1.41x faster.
That's amazing. Usually you have to pay a stability tax in training to get faster inference. Here they're kind of double dipping.
You are. The end-to-end speedup for the whole pipeline was about 1.16x for the 8B models they tested. But the paper makes a point to say that this speedup gets better as the models get bigger.
Right, because of the whole compute-bound versus memory-bound thing?
Exactly. Smaller models like 7B or 8B, they're often limited by memory bandwidth, just moving the data around. FP8 helps, but not linearly. But the huge models, 70B, 405B, they're compute-bound. They're just crunching numbers. And since FP8 literally doubles the compute throughput of the tensor cores, the larger your model, the closer you get to that theoretical 2x speedup.
So if you're a major lab training a 500 billion parameter reasoning model, JetRL is way more valuable to you than if you're just fine-tuning a 7B model on your own machine.
It's infrastructure-grade technology. If you are training at scale, you simply cannot afford to do full BF16 rollouts anymore. It's too slow, too expensive. And now we know you can't use the naive FP8 method because it breaks. So JetRL, or something very much like it, is going to become the default setting for training these advanced reasoning models.
It really reframes how we should think about quantization. For years, quantization was a post-training thing. You'd train your really smart model, and then you'd kind of lobotomize it slightly to make it fit on a phone.
Lobotomize is a bit harsh, but yeah, it's pretty accurate. It was an afterthought. Optimization was separate from learning.
But this paper is arguing that quantization has to be moved upstream. It needs to be part of the model's education.
It really connects to this broader philosophy we're seeing in robust machine learning. If you think of the model as a biological system, it adapts to its environment. And if that environment is noisy 8-bit math, and you train it in that environment from day one, it learns to thrive there. It learns its own forms of error correction. It learns not to depend on the 10th decimal place for its answers.
It makes the training mind and the inference body finally speak the same language again.
Yes. And it proves that we don't need perfect numerical precision to achieve perfect reasoning. We just need consistent numerical behavior.
Which, I mean, that opens up a pretty wild door for what comes next. We're all stressing about 16,000 tokens today, but the frontier labs are already talking about 100,000, maybe 1 million token context windows for infinite reasoning.
Right, and at that kind of scale, even FP8 might be too slow or too memory intensive for the rollouts.
So do we go even lower?
Well, NVIDIA's Blackwell architecture has native support for FP4, 4-bit floating point.
That feels incredibly low res, like trying to read a book through frosted glass.
It does. But, 2 years ago, people said training in FP8 was impossible because the gradients would vanish. JetRL shows that if you align the training and inference subgraphs correctly, the model just adapts. I think it's very, very likely that for these mega context reasoning models, we will see training pipelines move to FT4.
A 4-bit superintelligence.
As long as the training matches the rollout, the math says it's possible. The policy mismatch is the real enemy here, not the low precision itself.
That is a fascinating final thought. It's not the resolution of the image that matters, it's just whether your glasses match your eyes.
That's a great way to put it.
Thanks for joining us for this deep dive into JetRL. It's a technical but incredibly important paper that might just make these massive reasoning loops economically viable. I hope you enjoyed it.
A really clean solution. Thanks for tuning in.